All right, today we're going to continue on with 4.2. This is going to be more polynomial division. Basically, we're going to introduce the idea of using division to factor polynomials. And the nice thing is, kind of like you can think about polynomial division the same way you think about like number division, where you think about if you do 100 divided by 2, that's going to give you 50. You don't have a remainder. Versus if you did 101 divided by 2, that's 50.5. And because it doesn't go in evenly, it leaves a remainder. We're going to use that idea to deal with some factoring problems. And we're going to treat those factoring problems more in line with how we handle division, where we say, okay, if it goes in evenly, then, well, then the function has that as a factor. I mean, literally, it's factoring, like you say, 100 would factor to 2 times 2 times 5 times 5. It has a factor of 2. It has a factor of 5. Technically, it has 2 factors of each of those. So we're just using this idea of factors in factoring, but we're introducing it through division. So start with the division algorithm and the remainder theorem. This kind of puts it in context. Long division is the one that will always work. And here's the thing you need to get used to. Sorry. If you are ever trying to do polynomial division, long division always will work. You can always try that. Synthetic division only works in certain cases. Fortunately, though, it's the most common case that you typically run into. So synthetic division is great to know. You need to be able to do it. It's a nice shortcut on polynomial division, and it saves you a lot of work. But you also need to be able to do polynomial long division because you can't always check synthetic division. So, and then lastly, we're going to talk about how do you make a polynomial with these given roots, things like that. So the division algorithm, basically what it's going to transform a function into is it's going to take a polynomial, and if you think about like if you did 5 or 100 divided by 5, 5 goes in not 25 times, it goes in 20 times. My brain like stopped working for 2 seconds, and has a remainder of 0. Because this would be 100. Let's use 101. And it's going to have a remainder of 1. Which means 101 is equal to 20 times 5 plus 1. The difference is going to be, so you have your dividend analog, which would be the 101. And it's equal to the quotient, which is 20, and the divisor, which you're dividing by, plus a remainder. So the nice thing is if it goes in evenly, your remainder is 0. You don't say that. I guess you do. A lot of people do say there's no remainder, but when we say that, we say we're implying the remainder is 0. So just be a little bit careful with the wording. But what it's going to do is, notice these two, they're unique polynomials, q of x and r of x, that are the quotient and the remainder respectively. And d of x is also a polynomial. So if the remainder is 0, then you end up with q of x times d of x, which are two other polynomials, which means, after that dramatic suspense, you've factored it by doing this division process. And it also means if the remainder is 0 that, congratulations, you've factored it and found a root as well. Now, the degree of the remainder is always less than the degree of the divisor, or the remainder is 0, in which case you use the phrase divides evenly. This is kind of what we were talking about. And And basically what you've done is you found that Q and D would in fact be factors of P of X were the remainder to be 0. So some people, you can kind of think about this as it's almost like a power, not power reducing, because that's almost more like a trig term, but it reduces it from, like, say you had a third, or let's use a fifth degree for an example. You start with a fifth degree polynomial and you check this x minus k because you think that k, notice I say k and x minus k. If x minus k is a factor, then positive k is going to be a root. So if it factors to x plus 3, then you know that x equals negative 3 would be a root. So factor and roots, they have the sign switch. So just be aware of that. So you take this root k and you do the polynomial divided by x minus k. And you wind up with no remainder. So then what you end up with is a fourth degree polynomial times a first degree polynomial. So basically the remainder theorem is a specific case of your division algorithm to where the dividend is x minus k. So the remainder theorem is just a specific case and the one we're going to try and use the most. Sometimes we'll have to do like an x squared or an x cubed, but most of the time we're going to shoot for an x minus or x plus. All right, so in this case, we're going to try and use the remainder theorem to solve a problem, a factoring problem. So we want to divide the polynomial x squared plus 2x minus 24 by the polynomial x plus 6. So when you set it up exactly like your standard division. What you're dividing by goes on the outside, so x plus 6, which will then be divided by x squared plus 2x minus 24. And when you think about how you do standard division, you try and find how many times will it go into the largest place value. So you typically look at like, okay, like if it was 100, like we'll do the 5 going into 100. We'll do 101 again. Or let's do 106, for example. 5 can't go into 1, so I check how many times does 5 go into 10. Goes in twice with a remainder, and that leaves 0. And then we get 6, which will go in once with a remainder of 1. So you get 21 with a remainder of 1. With these, what you always do is you check the highest term of what you're dividing by, and you compare it with the highest term of the polynomial that you're dividing into. So my question is, really, how many times does x go into x squared? And there's always a way that you can determine this. You take what you're dividing into, you divide it by this term here, and that tells you that it will go in x times. Now this is where things get slightly different. Beforehand, you would do, like up here, it went in 2, so you do 2 times 5, and you get 10, and then you subtract. We're going to follow that same train of logic, but it's going to go x times x plus 6. So that's going to give us x times x is x squared. X times 6 is 6x, so we'll put it in line with the other x. And then this is the part that a lot of people tend to mess up on. when you subtract, you're subtracting this whole thing, which means you don't just change the sign of the first term, you change the sign of all of the terms. So this is going to be negative x minus 6x, not negative x squared plus 6x. And then when you do that, you wind up with, this becomes 0. 2x minus 6x gets me negative 4x. And then I have to bring down the negative 24. So it's kind of like you always tend to do. Now, I may be jumping the gun with the what part do I bring down. So let me save that for after. And the reason I'm going to save it for afterwards is because sometimes if you have a polynomial that doesn't stair step like x to the fifth, x to the fourth, x to the third, x squared, x, and then a constant, like maybe it goes x to the fifth, x to the fourth, but then goes down just to x and then the constant, what you bring down from that function may vary based on the components that you have. So next I need to check how many times does x go into negative 4x. And just as a reminder, this x is the one that I'm dividing by. I'm always dividing by the largest power in my divisor, or what I'm dividing by. So then this is equal to just negative 4. So I put negative 4 up here, and I'm going to do negative 4 times x, get negative 4x. You should always get it to where the first terms cancel out. That's usually what's going to happen. But then I end up with negative 4 times 6, which is going to be negative 24. And then notice I have a constant, so I'm going to bring down the constant term from the original. And then like before, that minus gets distributed everything, so this becomes plus 4x plus 24, which leaves us with a remainder of 0. And thus we're left with x squared plus 2x minus 24 is equal to x minus 4 times x plus 6, and then we can throw in the plus 0 for the remainder. So the polynomial x was divided by x minus k, which in our case was x plus 6. And so then we got our quotient plus our remainder, but because our remainder is 0, we've actually factored this polynomial. And you may look at this and go, okay, well, this was a very roundabout way to factor something that you might be able just to look at and see. This one's just an example. Typically when you do this, it's going to be because the thing has like an x to the fifth. And I consider myself pretty good at factoring, and I know friends that are better than I am at factoring. But you throw them something like x to the fifth, they're not going to just be able to immediately separate it into like a binomial and then a polynomial with 4 terms or something like that. Its usefulness will be shown later on. So always arrange the terms in descending order. So that means largest power down to smallest power. In our case, it worked out because it was already in that order. If it's not in that order, always make sure that you redo it into that order, because if you don't, it's going to be very bad. Then you divide the first term in the dividend by the first term in the divisor, and that gets you the first term of the quotient. That was what I was doing here. First term, first term. and then you multiply the entire divisor by the result, and then write it beneath the dividend, subtract the product from the dividend, and like I said, make sure you distribute the negative to all the terms. If you have 7 terms, then you distribute that negative to all 7. Bring down the rest, rinse and repeat until finally you get down to, well, notice the reason I stopped here was it was 0. Let's say this has come out to be 1. So it didn't divide evenly. If this, and notice this power, this is technically, you could say 0 times x to the 0 if you really wanted to. X to the 0 is less than x to the first, so that's why I stop. Once you get to the point where what you're dividing by is less than, or your remaining terms are less than what you're dividing by in terms of power, that's where you stop. Because say this would come out to be 1, I would get 1 over x, which equals the 1 over x. Can't really do much with that. So just be aware. This is why it says continue until the degree of the remainder is less than the degree of the divisor. Now here's one where it's going to be a lot more obvious to why you want to use long division. Divide this by this. Now notice one thing. 5, 4, 3, 2. Technically a constant is x to the 0. So we're missing an x to the first term. That's perfectly fine. You don't always have to have every term. But for a little bit of help, it's never a bad idea just to put this little placeholder term. Reason for that is just simply, I need a simple solution, or I need, not necessarily a simple solution, I need a simple way to make sure terms don't get jumbled, so I'm just going to use a placeholder. And again, if I add 0 to something, that doesn't change it. If you give me 0 times $1 million, I guess it's the thought that counts. I still do not have $1 million. So let's begin here. So first term here, 6x to the 5th divided by 2x cubed, or 2x squared. And again, I'm always pulling what's the highest power of what I'm dividing by, because that's going to tell me what I need to multiply it by. So 6 divided by 2 is 3. X to the 5th divided by x squared is x cubed. So I need 3x cubed. And this is going to be 3x cubed times 2x squared. Well, we know from over here that should be, sorry, my palm is like constantly knocking the thing out of this slide, 6x to the 5th. 3x cubed times negative x, negative 3x to the 4th, plus 3 times 3x cubed, which would be plus 9x cubed. And that's as far as it goes. So now we're going to subtract. And again, when you subtract, it changes every single sign. So 6x to the 5th becomes negative, minus 3x to the 4th becomes positive, positive 9x cubed becomes negative. And so when we do this, the whole point is, again, the first term should always cancel out. So this goes to 0, so we're good. Negative 5x to the 4th plus 3x to the 4th is negative 2x to the 4th. 10x cubed minus 9x cubed is going to be plus x cubed. And then, like I said, I will wait about what term do I bring down next. Because this one does do that stair step thing, or this is like you missed a step, so we need to make sure that whatever we bring down is actually going to show up next. So typically what you bring down comes after you've found what you're dividing by. So I need to do negative 2x to the 4th divided by 2x squared. negative 2 divided by 2 is negative 1. X to the fourth divided by x squared is negative x squared. So, now we get to multiplying. Negative x squared times 2x squared, negative 2x to the fourth. Those match up, so our work was correct. Negative x squared times negative x, positive x cubed, and then negative x squared times 3 minus 3x squared. And so because we ended up with an x squared term, we'll bring down our x squared term. And now this one kind of turned out interesting because when I go to subtract, which means I have to change all the signs, this becomes positive, this becomes negative, and this becomes positive. But now notice not only is the first term 0, so is the second term, because we do negative 2x to the fourth plus 2x to the fourth, cancels, gives us 0. And then x cubed minus x cubed gets us 0. And then negative 15x squared plus 3x squared is going to be negative 12x squared. So I only brought one number to the party. Okay, no worries. So now we do negative 12x squared divided by 2x squared. Negative 12 divided by 2 is negative 6, and x squared divided by x squared is 1. So then we just subtract off 6. And technically you could write it above the term that you're going by just to keep things straight. You don't have to, because this is going to end up being a polynomial. Because technically what you could say is it goes into the x cubed part 0 times because there was no x cubed. But if we multiply this, negative 6 times 2x squared, negative 12x squared, negative 6 times negative x, positive 6x, negative 6 times positive 3, negative 18. And so we can bring down our negative 19. Technically, we could also say we bring down 0x. But all in all, we subtract, which means all of these change signs. And so we get 0 from the first term, minus 6x, and then minus 1 because negative 19 plus 18. And so what we have is 2x squared minus x plus 3 when divided into all of this gives you 3x cubed minus x squared minus 6 with a remainder of negative 6x minus 1. What that means is this polynomial is not a factor of this polynomial because it did not divide in evenly. Our remainder was non-zero. So if this is what we were going after, was trying to find the root, this would be considered a failure. Because, well, that's definitely not 0. Yeah, so polynomial long division is straightforward. One common error is to forget to distribute the minus sign. That's why I think I may have gone overboard talking about it. But if you don't distribute that negative, things are just not going to work out. And you may have the right work, but if you drop that negative by accident, things are just going to fall apart really quick. Now, synthetic division is everybody's favorite. You know why? It's neater, it's nicer, it gets things done so much faster and in much cleaner of a way. The only problem is step 1. If the divisor is x minus k, write down k. First thing there, x minus k. That means if it's like x squared, stop thinking synthetic division. You can't use it. You're just kind of out of luck on it. You have to be able to use long division. I know it's a little bit more tedious. I know it's not as nice. And if you go, well, I haven't seen synthetic division, most people convert very quickly to the synthetic division method as being their favorite as soon as they see it. But, so basically what we're going to do is you write down k, followed by the coefficients of the dividend. So we don't even write down x cubed, x squared. We just write down, is it 3x squared? Cool, write down a 3. Then it's plus 5x. All right, write down plus 5. Minus 3. Just write down minus 3. And then you multiply k by the value placed on the bottom, and then place the product in the next column, the second row. And then you just add the values and you repeat. It's like a typewriter. It just keeps going and going. What happens is the numbers in the bottom row generate the coefficients of the quotient, and then the remainder is the final value. And you end up reducing the degree by 1. So we'll do it with 2 examples. And this is being used to determine is the given factor, or is the given root k, is the given number k a root of the polynomial? Which is also asking, is x minus k a factor of the polynomial? Be aware of how things are asked in different ways. So, here's the first polynomial. And so notice the way this is written. K is 5, goes in this box at the top left. And then we wrote down, this was your x to the 4th, x cubed, x squared, x, and then your constant. So what's going to happen is the first term, or the first coefficient, just comes down. Then what you do is it's almost kind of like an assembly line. You do 5 times negative 2, that goes here. And then remember, this is the thing you have to be careful of. Add these values, not subtract. You don't have to change any sign. Add them. So 5 times negative 2 is negative 10. 11 plus negative 10 is 1. Then you do 5 times 1 is 5. Add those two together. You get 0. 0 times 5 is, well, 0. Negative 3 plus 5, or negative 3 plus 0 is negative 3. 5 times 5 times negative 3 is negative 15. And 15 minus 15 is 0. And one thing I typically do is I always put the last number in almost kind of like basically the reverse of where your tested root sits, to indicate that we're at the end of the problem and that this is the remainder. And so the remainder is 0. Therefore, and that's what those 3 little dots mean, k equals 5 is a root. Of p of x. Let me be specific. It could be a root for a tree, but specifically it's a root of our given polynomial p of x. And then what this means is p of x equals x minus 5, and this is one other thing. K is equal to 5. That means if the root is positive 5, then when you write it as a factor, it's x minus 5. And now when we construct our polynomial, remember we said that the degree decreases by 1. This was x to the 4th. so this is now x cubed. This is x cubed, so this is now x squared. This is x squared, this is now x. This was x, this is now our constant. And so because of that, it becomes x minus 5 times negative 2x cubed plus x squared minus 3. And then plus 0 because there's no remainder. But the key thing is it is factored now. And it's factored into something a lot nicer than what we've had in the past. So this is why probably as soon as you see this, you go, okay, I'm immediately dumping everything about long division from my brain. Please don't do that. If you do, it's going to make your life much more difficult because some things cannot be done with synthetic division. Again, you have to be testing a single root. Now, the placeholders were optional when we were doing long division. They are a necessity when we do synthetic division. Because remember I said the process was bring the number down, multiply by what you're dividing by, or multiply by your k value, put it in the next slot, add down, rinse, and repeat until the end. The thing is that rinse and repeat part has to go for every single space. It can't just be what's written down. So like p of x, the reason it's chosen is, notice it's 3x to the 8th plus 9x to the 7th. Jump straight down to minus x cubed minus 3x squared plus x minus 1. So now you're in a bit of trouble because now you're missing x to the 6th through x to the 4th. So you have those three terms missing. When we write this, we have to include these zeros. If you don't, well, you get the wrong answer. Because the way synthetic division is designed, it's basically an algorithm. And it has to check every place of x to the n from whatever your n is all the way down to your constant. So when you jump from x to the 8th, x to the 7th, down to x to the 3rd, basically you're kind of confusing the algorithm because it goes, wait a minute, I'm supposed to just be counting down one at a time. And also what happens is, remember, when you're making the polynomial down here, it's reducing it by 1. So this was x to the 8th. Then whatever term I get here is x to the 7th. This is x to the 7th. Whatever term I get down here is going to be x to the 6th. But then if I jump down here to x cubed, because you're just supposed to be going descending, if you didn't write these zeros, then your algorithm's going to go, wait a minute, isn't this supposed to be like the x to the 6th slot? So it's going to be very confusing for what goes there. So just be very aware as to what happens and what you need from it. So we have placeholders for x to the 6th, x to the 5th, x to the 4th, before we get down to our terms that are written in the problem. So if we start here, so we bring down 3. Negative 3 times 3 is negative 9. Add those together, we get 0. Negative 3 times 0 is 0. Add that down, we get 0. Negative 3 times 0, again, 0. Add here. This one's a little boring for a segment. All right, and then finally 0. And then we get negative 1 plus 0 is negative 1. Okay, good. Something we can work with. Negative 3 times negative 1 is positive 3. So that gets us yet another 0. Negative 3 times 0 is 0. 1 times, sorry, 1 times, or add 1 times negative 3 is, well, negative 3. And we end up with a remainder of negative 4. So, not quite. So this is a case where it's not a 0. And that's okay. You don't always end up with a 0. Sometimes it's just a test. If we go through, just double check. Brought down 3. Negative 3 times 3. Negative 9. 0. Get zeros for all those. 0 times 0. Bring down to the negative 1. Positive 3. That becomes 0. Add those. And so you get the idea. So in this case, negative 3 was not a... Sorry, negative 3 was not negative 3 is not a root of the given polynomial. And if you look at this one and go, well, everything seemed to work out fine even if I didn't have the placeholders. Try x to the 4th minus 1. And try k equals negative 1. You know negative 1 is a root. Try it without this and see what happens. Actually, we can do that right quick. So what it should be is 1, 0, 0. Because x to the 4th cubed, squared. We need a first, and then our constant. So we're going to test negative 1. So I bring down 1. And then 1 times negative 1 is negative 1. Add that. I get negative 1. Multiply. I get positive 1. Add 0 and 1. Then multiply again. I get negative 1. Add. I get negative 1. Negative 1 times negative 1 is positive 1. And so there we go. I get that it's a root. So this is the correct way. Now let's do the incorrect way, where I go negative 1, and then I ignore the rules, and I say, okay, well, I have 1, and I have minus 1. I'm just going to test those two. Bring down the 1. I get 1. Negative 1 times 1 is negative 1. And I get negative 2. And so I say that negative 1 is not a root of x to the 4th minus 1. And that very clearly is an incorrect statement, because you can just plug in negative 1 and figure that one out. So those placeholders are a necessity. They're not optional. When you do long division, they are optional because they're there as placeholders. They're there to not necessarily incentivize you to not make a mistake. They're there to help keep things lined up. Versus here, because of the way that the synthetic division algorithm technically works, it needs to have the coefficients of every power of x between n and your constant. So if some of those are zeros, you have to write those zeros. Because like with this one, we went from x to the 7th to x cubed, so we miss x to the 6th, x to the 5th, and x to the 4th. You have to include those. Because of the wording of it, and specifically the way it's designed, it's going through and doing that check on all of them. So if I have not preached this enough, hopefully that mistake will not be made now. All right, so finally, example 5, construct polynomials. So I need a third degree polynomial with the given zeros, negative 3, 2, and 5, And it also has to have the property that as x goes to infinity, the function is going to negative infinity. And then the fourth degree with the given roots and a specific y-intercept. So one thing, these will be kind of like two things where we kind of introduce how do you make a polynomial go the direction you want it to. So if we put these things together, so we need x equals -3, 2, and 5. So roots -3, 2, and 5. And then it goes to negative infinity. Got a weird curve on that. So then we also need p of x goes to negative infinity as x goes towards positive infinity. So if we put the roots together, again, -3 is a root, 2 is a root, and 5 is a root. So you write it as x minus that root. So every plus becomes a minus, every minus becomes a plus. But does this happen? The second part. As x goes to infinity, does negative infinity, or does p of x go to negative infinity? Remember to do our check for p of x, we just multiply all of our powers of x and how many times they appear. We just drop the pluses. So this is x times x times x. So this is x cubed. So remember, this is n is odd, and a sub n is equal to 1. So this is odd with a positive leading coefficient, which means it's going to do something like this. But notice as x goes towards positive infinity, this function goes towards positive infinity. That's the opposite of what we want. So to course correct it, I need to just switch the direction. To switch the direction, I just multiply by -1. So I get p of x is equal to negative x plus 3 times x minus 2 times x minus 5. And if you multiplied it out, which you don't have to, you would wind up with this polynomial. Now the second one, let's see, it was a fourth degree with -5, -2, 1, and 3, and had a y-intercept of 0, 15. So like before, you've got your roots of -5, -2, +1, and +3, and it goes through 0, 15. So roots are handled. Nice. But if we plug in 0, well, we get 30. That's not good. So your first thought might be, oh, well, what if I just subtract 15? That would help, right? Not really. And if you need to look at it for a second and go, okay, why does this not work? Now if I plug in -5, I get -15, not 0. So remember, this is a vertical shift. It just is in the negative direction. So it's taking this whole polynomial and shifted it down by 15 units, which means your original roots are now just null and void. So like before where we multiplied by -1, if this is 30 when I plug in 0, don't subtract, divide 15. Or divide by a half, sorry. because it's coming out to be 30. So if I want it to stay with those roots, but now have a 30, or have a multiple, not a multiple, words are hard, to have a y-intercept of 15, if it's coming out to be 30, I just need to multiply the whole thing by a half. And if I do that, now notice if I plug in 0, I get 5 times 2 times -1 times -3, which does get me 30, but now this 1/2 out front, that counteracts it. And so now I've got everything I need. What you're always going to use to meet specific y-intercept conditions or directional conditions as to the end behavior are always going to be these multiples out front of your polynomial. So anytime you have the given roots and then some other request about it, like how the end behavior goes or this, that, or whatnot, always go to what do I need to multiply out front to make that happen. And that makes things a little bit easier. And so with that, we'll keep continuing on through chapter 4 next time.